Hello, we are continuing with our discussion on the differential equations and as I mentioned at the end of the previous video that we will be discussing the first order, the second order differential equations followed by the homogeneous and inhomogeneous linear equations uh, and they will be of degree 1 and to start off with we begin with the first order differential equation in its simplest form. So the first order differential equation and we are through to the simplest form, that is now the simplest form of the first order differential equation is as we have already studied the first order derivative, that is dy by dx is equal to some fx. This is the simplest form, and this is easy to find the solution, that is y is equal to the integration of fx over dx, and then we are going to end up with a constant, an arbitrary constant added to that as well. So this is simply the solution to the simplest form of the first order differential equation. And now we quickly move over to the second form. The second case being equations with variable separable, as you can see over here. The second case, that is the variable separable that we had mentioned. So equations with variable separable. Now in this we get the kind of equation which involves functions of two types. That is, let us say we have an equation where f1x, as a function of x obviously, is multiplied to g2y as a function of y, finally multiplied to dx, and then we have f2x. f2x again is a function of x, and g2 g1 is there, g1y. So g's are the function of y and f's are the function of x, but they are not the same. One is f1, the other one is f2. One is g1 and the other one is g2, and this is multiplied to dy, and it's a homogeneous equation is equal to 0. Now how do we approach this? Well, because they are the same terms that we see, so we can, not the same in the sense that they are different functions obviously, but there's a form of repetition over here. So what we can get from this is that we divide this equation by f2x and g2y, that is. So f2x and g2y, if we divide the above function, then what do we get? Now the g2y is going to get cancelled in the first term, and what we are left with is f1x divided by f2x and the dx intact. And in the second term, what we are going to cancel out is the f2x. So we will be left with g1y, and this is g2y, and that is multiplied with dy. So on the right hand side obviously there was 0, so no problems with that. So now we have separated these variables that were there involving different functions. Now they will be easier to integrate, so we can just integrate it. f1x, f2x, dx, it will be integrated over x over dx, that is, and on to the right hand side we can keep the y on the left and the x on the right. That doesn't really make a difference. Still you are going to end up with a positive sign on one side and the negative sign on the other side. So I have just used this case where I have taken the y onto the right hand side. You may keep the y on the left, and which is the general notion that we consider. And obviously this is going to end up with an arbitrary integration constant with that. Now this equation is a variable separable equation because we have separated the x and the y terms. So now we are through with the solutions easily. Then we consider the third type, which is the exact equation. If you remember the list that is there on the previous page, so the exact equation is of the type, or an equation is said to be exact if it is written in the form m of xy multiplied with dx plus n of xy multiplied with dy to be equal to 0, and this equation will be exact if it this equation will be exact equation if it can be expressed as a complete differential form, that is df of xy, which is equal to 0, of course, because there was 0 on the right hand side. So that means that out of those two terms that we have over there, that is one multiplied to dx and the other multiplied to dy, can be taken to the form of df, which is a function of x and y. And how do we do that? Let's see if we have any example which will help us understand that. Now obviously if we integrate this term, that is df xy, then we are going to end up with f of xy on the left hand side and c, that is a constant, on the right hand side. So this is for with the integration, the solution, that is, which is obtained out of the integration. Now let's see what conditions that we can come up with. Now if df that you see is a function of x and y, so df of xy is simply the partial derivative of f with respect to x multiplied with dx plus the partial derivative of f with respect to y multiplied with dy. And if we compare these two equations, now this is obviously on the right hand side there was 0, so this on the right hand side is going to have 0 as well. So if we compare these two equations, what we have is m to be equal to del f by del x and n to be equal to del f by del y. And with this comparison available to us, we can further take, because both of them are functions of x and y, so del m by del y is going to give me del square f divided by del x del y, and for del n divided by del x we are having del square f divided by del y del x. It doesn't matter if we are taking the derivative firstly with respect to x and then we are taking the partial derivative with respect to y for f, because it is depending on both x and y. So the right hand side terms, they are the same, and therefore from this what we conclude is that the left hand sides must be the same, and this is exactly the essential or the necessary condition for an equation of the form m dx n dy to be exact. So this is the necessary condition that the given equation is an exact equation. Now if we were to integrate f with respect to or in terms of x, then we will have the integration constant completely dependent on y, and if we integrate f with respect to y, then we'll have an integration constant completely dependent on x. So that is how we that depends on how we choose the integration, or on what basis we choose the integration. Moving ahead, we discuss the inexact differential equation. Now, an inexact differential equation is obviously one which is not exact, but it is ideal that we take it to the exact form for us to integrate it in a efficient way. And in order to convert an inexact differential equation to an exact one, we multiply it by a factor which is known as the integrating factor. So this integrating factor must be multiplied to that inexact equation to make it an exact one. Now, from the previous discussion, as we have seen that del f by del x is equal to m, and del f by del y is equal to n. Now let us suppose take the ratio of those two terms. So del f by del x is to del f by del y is going to give us m divided by n. We can very easily multiply a constant over here, that is a mu. It may be a variable, or uh, you know, it may be dependent on x or may not be dependent on x. uh, that's a separate case. So mu m divided by mu n makes no difference, but it finally makes a difference to the initial equation. That is, if this is the case, then we have del f by del x now to be equal to mu m, and del f by del y now to be equal to mu n, and then we have the m dx plus n dx, that is the df that we had of xy, to be equal to mu m dx plus mu n dy, which is equal to mu m dx plus n dy. This mu that was multiplied is called as the integrating factor. We can further multiply this equation that we have over here with another term, or another integrating factor, which means that the mu is any arbitrary integrating factor, but there can be many integrating factors which can be multiplied to the given term or given equation, differential equation that is, to make it an exact one from its inexact form. Now let's determine some of the integrating factors that we can multiply. First up, we'll discuss the integrating factor by inspection. So we discuss various methods in which we are obtaining those integrating factors, and we first of all determine the integrating factor by inspection. Now, if we consider an equation of the form x dy minus y dx, now, and we multiply it with an integrating factor, suppose here we have the ifs, and the integrating factor supposedly in this case is 1 by x squared. Now this 1 by x squared over here, when multiplied to this equation, now this is inexact for sure, because if you observe it closely, then this particular term here, you have this is equal to n and this is equal to m. So del m by del y is going to give me -1, while del n by del x is going to give me plus 1. So they are not equal, and hence this is not an exact equation. So we multiply it with an integrating factor, let us say of the form 1 by x squared, and what do we end up with? Do we end up with an exact form? Let's see for ourselves. We have x dy minus y dx, which was the initial equation, which is multiplied with x squared. Now if you observe this, this is of the form u by v form, and with that u by v form, we have x instead of v and we have y instead of u. So v du minus u dv divided by v squared is just the differential of u by v. So this is d of y by x, which is a complete derivative single df, here f being equal to y by x. So this is of the first kind. We continue with that same equation, that is x dy and y dx, and we now multiply it with 1 by y squared. Now with 1 by y squared multiplied to it, we have minus y dx plus x dy divided by y squared, and so this now becomes d of minus x by y, isn't it? Because y is now the v term, but it's obviously in the negative sense, so that is why it is to be taken as a minus x by y. Then again, if we multiply further the same case, we are multiplying with another integrating factor, which is 1 by xy. Now 1 by xy is going to give me the, if we are dividing x dy by xy, then the x's get cancelled out and we have dy by y, minus y dx divided by xy, the y's get cancelled out, so we have dx divided by x. Now integration, or the integration would give me obviously the logarithmic form, so that is why we have d of the logarithm of y by x, because x is negative, so it's going to be in the denominator, so the derivative of ln of y by x is what we are going to get. Then we take another, supposedly we divide this entire equation by x squared plus y squared. Then we are going to get x dy minus y dx divided by x squared plus y squared, which is equal to derivative of the tangent inverse of y by x. And if, as opposed to just differentiate or just dividing it by xy, we divide it with xy to the power n, raised to the power n, then with obviously for n is equal to 1, we are going to end up with this same thing, 1 by xy. Here we are taking n not equal to 1 or any higher power of n on the same thing, that is x dy minus y dx. So let's take for a change, we consider x dy plus y dx in this case. So now with x dy plus y dx divided by xy raised to the power n, we have the derivative of the form d of minus 1. You can check for yourself, it's pretty easy to consider. You can take it the reverse way, taking the differential, and if you end up on the left hand side, that is x dy plus y dx divided by x y to the power n, then also you are through with the analysis. So this is the case where n is not equal to 1, as we have taken. Now for n is equal to 1, then because there is a plus sign over there instead of the minus as in the previous case over here, we are going to end up with d of ln of x multiplied with y instead of y divided by x or x divided by y, as the case may be. So this is the integrating factors. So as you can see, for the first four cases that we saw, x dy minus y dx, there were plenty of integrating factors that we can have for a given equation. Likewise, we can calculate the integrating factor. There are methods of calculating the integrating factors as well. Let's see a few of them. Now, if m dx and n dy is chosen such that we have del m by del y minus del n by del x entirely divided with n which is multiplied to dy is equal to function of x, then we have the integrating factor in this case to be equal to e to the power integration of fx over dx. Now if we have this del m by del y minus del n by del x for m dx plus n dy to be divided by m, which is giving me a function of y, then the integrating factor in this case is going to be, these are predetermined, so we need not be worried about methods of finding them. We just need to know the rules of finding them. So this is e to the power integration of g of y over dy, but negative of it. Now had this equation had minus gy in this case, then we would have ended with plus gy and so on. And then if the equation is the fourth kind, if the equation m dx plus n dy, which is equal to 0, is obviously homogeneous, and mx plus ny is not equal to 0, then we have the integrating factor to be equal to 1 by mx plus ny, which is this term. And if the equation, the fifth one, that is, if m dx plus n dy is of the form, now this is equal to 0, is of the form y of f of xy dx plus x g of xy, another function, multiplied with dy to be equal to 0, where f is not equal to g, of course, both those functions, then we have the integrating factor to be equal to 1 by xy f minus g. So if f was equal to g, then the denominator would go to 0 and this would be undefined. So that is why f must not be equal to g. So if we have xy, in case f was equal to g, then those two terms would have been common, and with the 0 on the right hand side, they would have vanished. But in this case, we have the integrating factor to be equal to 1 by xy times of f minus g, and if you observe it closely, it is simply equal to 1 by mx minus ny, as m was equal to yf, that was multiplied to x, and n was equal to xg, that was multiplied to y in the denominator there. So all you have xy on both those terms, and they can be taken out common, and you're left with f minus g. So that is more or less the another way of another rule set for obtaining the integrating factor. like I had already mentioned, we can have multiple integrating factors for a given differential equation. Then with our discussion on the first order differential equation, we are after the inexact equations, we are headed to the general first order differential equation. So in case of the general first order differential equation, we are having it of the form, the general form, that is where we have some dy by dx plus p of x multiplied to y is equal to qx. Now these px and qx obviously are the functions of x, and this can be solved by determining an integrating factor such that when it is multiplied it reduces the equation. Now we consider an integrating factor mu which is multiplied to give or reduce the equation, reducing the equation to the form d by dy of mu of y to be equal to mu of q. Let's see where we are getting. So let's continue with this, where mu and y are two separate variables which are integrated over y. So you have d mu divided by d, oh, did I write x? Did I write y? So this is x. Let me rectify that. Okay, so this is d mu by dx multiplied to y, which is the constant term, plus mu being constant dy by dx is equal to mu q. Then we have dy by dx plus, well, this can be put together as 1 by mu just by dividing that mu, d mu divided by dx of y multiplied to y, that is equal to q. Remember, mu has been divided. So now the equations that you see over here and the first one over here, if you take a close look at those equations, now they're somewhat similar, and with them being similar we can compare them, and on comparison what we are getting is we are getting 1 by mu d mu by dx to be equal to px, and obviously that will result in something of this form: d mu by mu is equal to px times of dx, and on further integrating it we'll get mu and the ln of it to be equal to px dx, or we have mu, the integrating factor, and now we are coming back to some familiar term over here, e to the power px dx. Now remember, this was the type of integrating factor that we had earlier obtained, so the integrating factor here comes back to that form that we had obtained previously. Now, so the equation over here that we had assumed, now if we are to take the equation, that equation into account, we are going to get considering the case of mu, we are going to get the derivative or that expression as mu y to be equal to integration of mu q dx plus c. And finally All this is possible because we now know the value of mu from this. Now from this we finally have the solution of the value of y, that is y is equal to 1 by mu. It's always uh, necessary, it's always the case of finding the solution for a given differential equation, and here we have it. So it is of the form 1 by mu. Now with the value of mu having been determined by the above equation, this one, that is 1 by mu times of mu q dx plus c by mu is what we have as the solution for the general first order differential equation. The last part of the last form of the differential equation involves the Jacob-Bernoulli equation. Now the Jacob-Bernoulli equation is an interesting one because if you observe this, which I am writing just now, pxy is equal to qx and y to the power n. Interestingly, we have a higher power of y, which is not the case in case of linear equations. So this is a non-linear equation. However, it can be reduced to a linear one, and then we can have the solution. So if we divide both the sides by y to the power n, so what do we end up with? So if we divide both the sides, dividing by y to the power n, what we get is y to the power minus n dy by dx plus, here we have p y to the power 1 minus n, and on the right hand side we are left with q. Now we substitute v. Let v be equal to this fellow y to the power 1 minus n. Then dv by dx is going to be 1 minus n y to the power minus n dy by dx, which also gives me y to the power minus n dy by dx to be equal to 1 divided by 1 minus n dv by dx. Now we put all the terms that we have obtained in this equation over here. Now as you can see, y to the power minus n dy by dx is simply this thing, so we put it over here, 1 by 1 minus n dv by dx, and then we have pv and we have q. Now it looks like we are getting to the linear form where we can just multiply this entire thing with the 1 minus n factor, and let's, for our convenience, take this 1 minus n into p as p1 and 1 minus n into q as q1. Now we have a linear differential equation where p1 is obviously equal to 1 minus n times of p, and q1 is 1 minus n times of q. So we have reduced it to a linear differential equation, and now we have the solution of it. As you know that y was equal to 1 by mu times, similarly v is equal to 1 by mu times, so this is the solution. V is equal to 1 by mu times of mu, q, instead of q we have q1 dx, plus we have c divided by mu. Now this is the solution, and we have also the value of mu over here to be equal to e to the power p1 dx, or p1, you can substitute the value over there as 1 minus n times of p. 1 minus n being a constant can be taken out, and then we can determine the solution. We having known the value of v, we can determine the value of y, because y is equal to v to the power 1 by n minus 1. So finally we have y to be equal to v from this equation. Where was it we had considered? Yeah, this one. So from this we have y to be equal to v to the power 1 by 1 minus n. So all of this becomes pretty simple when we are converting the non-linear equation to a linear one. We'll be having one more video for sure for the linear second order linear differential equation, the final installment to the differential equation playlist, and we'll end this and we'll be trying a few numericals as well to add to those videos further, but that will be in the upcoming videos. Till then, thank you for watching.